Hello, this video is dedicated to solidify the load shear bending diagram again, however, with introducing new concepts. So let's name this. It's going to be load shear bending. Example 3. Okay. So today we're going to introduce this example. We're going to have a beam, have a distribute load. That's something new, isn't it? So we have a distribute load right here. And this time the intensity is 5 kilonewton per meter. And also we have a right in this point, we have another force. This is concentrated. That is 15 kilonewton. In addition, we have a concentrated moment, 80 kilonewton meter at point A. And A is going to be a roller support. And at point B is a pin support. So what should we do first for this problem? We need to find reaction support at A and B. So in order to do that, we're going to look at this entire FBD, number 1. So for roller support, we're going to have A going Y direction and B have X and Y. And here I'm just ignore the X direction because you already know that's equal to 0. So in order to find A in one step, we're going to do moment about B. Moment about B. This 80 kilonewton meter, that's a moment itself, so that's going to go to this equation. And since it's clockwise rotation, it's going to be negative. Then we will have this 15 kilonewton, this concentrated load, rotating about B. And we need to give the dimension. So here dimension is 5 meters. Okay, so knowing that, we're going to continue our equation, 15 kilonewton times 5, and that's counterclockwise, being positive. Then we have this distribute load. We're going to find its equivalent, which is going to be the area will be 5 times 5, right? Base is 5. And distribute load intensity is 5. So that's going to be right in the middle since it's rectangle. So that's going to give us 25 kilonewton. All right. So knowing that, that's our 25. Then it's right in the middle. So it's going to be 2.5, half of the 5 meter right here. Then that's counterclockwise. So that's going to be positive. So the last thing in our equation is this force A. So this A rotating about B, its entire length of the beam, so that's a 10 and it's clockwise, so that's going to be negative, that equal to 0. So solving this, we'll get answer for our A. So plug into the calculator. I got 5.75 for A kilonewton. So knowing A is this value, we can quickly find out the force at B. So force at y direction will give us 5.75. That's reaction support at A minus this concentrated load 15 minus this equivalent of distributed load 25, then plus our reaction support at B. Then we can calculate our B, and the answer I have is 34.25 kilonewton. Okay, that's our first step. I mean, we can solve this in statics, nothing new yet, right? So now we're going to look at each section. By looking at this entire FBD number 1, it looks like there's 2 sections. The first section is going to be right here, right? And the second section will be this part, the second half. So we already know at each section you're going to have a different internal loading expression. So first thing we're going to do is we're going to see if X is going to be ranged from 0 to 5, the first half. What will be our N and V and M? In order to do so, we're going to make our cut. If we're going to make our first cut anywhere for the first half, that's where we cut. Then we're going to draw our FBD number 2. So for FBD number 2, we're going to have, I'm going to use the left section because that's the simplest solution, right, to solve it. Left for this problem, it's going to be way easier on the right. Hope you agree with me on that. And then what do we have? We'll have at point A, we already know this reaction. A is 5.75. Then we also have external bending moment, 80 kilonewton meter. Then we come up to this where we cut. We'll have this normal force to make a tension to be positive, to make this part of the section to rotate clockwise. So this V gonna be going downward, and to make a smile bending, so M going this way. Now we're going to solve all 3 of them. First thing, you already know the N is going to be equal to 0. Then force at y direction will have 5.75 going upward minus this V, since it's going downward, that equals 0. You calculate V to be 5.75. Then we're going to use moment about where we cut at this point. So we'll have this moment itself, it's clockwise, so it's going to be negative 80. Then we have this 5.75 times, what's the distance from here to here? We already have seen many times, so it's going to be x, right? It's going to be times x, and that's clockwise rotation, so that's negative. Then continue, we'll have this internal bending moment you are solving, and it's happened to be counterclockwise, so that would be plus m, that equals 0. So from this equation, we get expression for this internal bending moment. That will be equal to 5.75x plus 80. So break up those answers. Okay. So what we have gotten is basically for the first half of the beam. Now we know what we're going to solve next, right? So I'm going to use this space. Our x range is going to be from 5 to 10. So it's going to be this section now. For this section, we're going to make a cut to find our internal loading. So here, I'm going to use this green marker here. Imagine we're going to cut anywhere for this section. So imagine if I make a cut right here. Okay, we have a choice to use left section or right section, and I think right will be easier. So let's go with right. That comes our FBD number 3. So our right section, we will have this end is B, where we cut this green line. Let's go ahead and draw all the forces on there. We know the force at B is 34.25 kilonewton. Then we also look at this part of section. What's actually on there? What force is on there? It's actually this distributed load that's on there. So that's something new for this problem. We have distributed load. You might wonder, why don't we use this 25 kilonewton? This is a concentrated load. That's true. This concentrated load help us to solve reaction support in the first step. But in reality, in this part of the beam is actually distributed load, right? And distributed load, it's how long is this? Okay, I think we have discovered this in the previous video. Remember, your A is way here, and where we cut, that's a random space, and that's going to be your X. So this length will be your entire length, 10 minus X. Okay, so knowing that, we're going to continue finish our FBD number 3. We'll have this where you cut internally, so we're going to have this normal force. Also, we're going to have this V. Also, the bending moment. So all the 3. And N will be equal to 0. Force IY direction. We'll have V going up positive. We'll also have this B going up 34.25 equal to 0. Then we calculate our shear V is negative 34.25 kilonewton. Okay. The last thing to solve is the moment where we cut. Okay, so it's at this point. First thing, this internal bending you're solving, it's clockwise rotation, so that will be negative M. Then we need to figure out the distributed load. What is going to be the area underneath this distributed load? That will be the base 10 minus X times the intensity. What's the intensity? 5 kilonewton meter times 5. That's going to be the concentrated load. And where that will be located will be right in the middle of this rectangular section. So knowing that, we have this 10 minus X times 5. That's our equivalent concentrated load times moment of arm. What's the moment of arm? This is where we cut. Moment of arm for this will be this distance. That will be half, right? That will be half of 10 minus X. Okay, because this entire length is 10 minus X. So that's, again, something new. So be aware of those new points, new elements embedded in this problem. Now we're going to look at the last one, which is our force 34.25. And the moment of arm for that will be 10 minus X. And that is making it counterclockwise, so it's going to be plus And oh, I forgot to think about the sign here for this equivalent force. So that's going down and rotating, and that will be giving us clockwise rotation. So that's negative. So all those going to give us equal to 0. While we are solving, we're trying to find the m. Oops. So m, we're solving, is going to be equal to negative 10 minus x squared times 5 over 2. Then plus 34.25 10 minus x. Okay, so if we're going to simplify that, we'll get something like this. Should we try? Okay, let's go ahead then. So that'd be 2.5, negative 2.5, and 10 minus x squared, that's going to be 100 minus 20x plus x squared, then plus 342.5 minus 34.25x. Then your power of 2 term will be negative 2.5 x squared, and power of 1 term, you have negative 2.5 times 20. That will give us 50. Then you have another one, the minus 34.25. That will combine together. That will be 15.75x. Then let's look at our constant term. This will give us 250, negative 250 plus 342. The answer I have here is 92.5. And all those going to be our bending moment have a unit of kilonewton meter. So that's our bending moment. Okay, so we have everything ready. Now we're going to put them into our load shear bending diagram, right? So load shear bending diagram. That's the last step to show this in a graphical way. So for load, we'll have this beam. We have a concentrated load in the middle. Then we have distributed load. The concentrated load is 15 kilonewton. And distributed load gives us 5 kilonewton per meter. We also have a external moment, 80 kilonewton meter. We calculate the A is 5.75. At point B, reaction support is 34.25 kilonewton. All right, that's our load, our shear. For the first half, between 0 and 5, our shear is 5.75, so which means it's a constant value. However, when you get into the second half, we got expression for V is negative 34.25, so it's jumped down to okay. Well, hold on for a second. I just spotted the error I made. So let's go back to this shear force. You probably have already noticed the mistake earlier. So when we look at this four-sided y equation, we have this shear V going upward, and we also have this support reaction going upward, plus, but I'm missing which one? I'm missing this equivalent concentrated load, so I need to add that into the equation. So here we go. That's going to be minus 10 minus x times 5. So this would be wrong. And the true expression for V, when you're solving it, will be negative 34.25 plus 5 times 10 minus x. So that would be equal to negative 5x. Here is 50 and here is minus 34.25. That will give us 15.75. Okay, so apologize for the mistake. That's going to be our shear expression. So now we are going to draw that function into this shear diagram. You realize it's a linear function, and like how we normally do, we're going to put our beginning point and end point. So the beginning point is when x equals 5. End point is when x equals to 10, right? That's our dimension, 5 to 10. So when you put x equal to 5, our v, 5 times 5, negative 25, then plus 15.75. What do we get? So you will get negative 9.25. Same fashion, when you put x equal to 10 here, so 5 times 10, negative 50, plus 15.75, that's going to give us a value of v equal to negative 34.25. That defines the beginning and ending point. So beginning point is negative 9.25. Again, this is not drawn to scale. And the last point is going to be negative 34.25. And it's a linear function, so we're going to connect in the dot. Okay, so to complete this, at this point, we're going to just jump downward. And here close end, we'll have our shear diagram. This is nothing, doesn't look like anything we have drawn before, right? So the problem starting to become more complex, and however the logic, the procedure, it's same. Now let's look at our last tier, which is our bending. Okay, our bending, first bending equation is right here. So again, put our beginning point, first half, x equal to 0, and ending is 5. So when x equal to 0, our m equal to 80. When x equal to 5, this is going to give us the bending. So 5 times 5.75, then plus 80. That gives us 108.75 kilonewton meter. Okay, so knowing those beginning points and ending point, and we know it's linear because it's a parallel one. So starting from 80 and end at x equal to 5 meter, and this m, this point bending is 108.75 kilonewton meter. It's a linear line. Okay. Then let's go to the second half. We have this quadratic equation, and in order to find our beginning and end point, we're going to see x equal to 5 and x equal to 10. When you plug it in, here you definitely need your calculator. So when you plug it in, when x equal to 5, my answer given to me is 108.75. I encourage you to pause the video and to check your calculation. And the second one, your m equal to when x equal to 10, the answer will give us to be 0. Again, pause and check. So beginning point is happen to be same point 108.75. The end point is 0. However, this is not a linear line anymore. This is a quadratic equation. And it's a quadratic equation, and since there's a negative in front of it, this is actually going to curve down. So I'm going to make it dramatic. It's going to be like this. So it's a quadratic equation. Okay. So this defines our bending moment curve look like for this beam. What's important point, what's interesting point we're looking at will be this point, which is a peak. That's going to be our maximum bending. For this problem will be 108.75 kilonewton meter. Okay, so that concludes this problem. This problem have two sections and with addition of distributed load. And so this is something for you to review for distributed load, especially for where the moment of arm is, etc. Now, there's one more thing I want you to start thinking about it. So this is something I want you to look. This shear is 5.75 and bending is this value. Did you notice if I were to do derivative of bending moment with respect to x? So if we were to do derivative of this equation, will we get 5.75? Yes, which happened to be our shear. Interesting, huh? Now let's see if this finding applies to the second half as well. So if we were trying to do the derivative m over x for this quadratic expression, this first term is going to be negative 2.5 times 2x. That's negative 5x. The second term will be just 15.75. Is that equal to your shear right here? It's the same. So one very interesting thing we're about to discover is derivative of bending is going to be equal to shear. Yeah, I'm going to put rainbow color around it because it's that important. So in another way, you could write this integration of shear is going to be equal to your bending, right? So that's something very interesting, and that will lead us to the next topic in the next video. So as right now, we discovered the derivative of bending is equal to shear, and in other words, if you will integrate your shear, you are going to get your bending. So let's go. I suggest you at this point to go back to the previous videos of the other two examples we did for low shear bending diagram. See if this finding applies to them as well. And you will be happy to find out this actually is consistent. So go ahead, happy exploring. See you next time.